comparing three or more means, and we could use the mean test from before, but here we use something called ANOVA, which is analysis of variance. That's what it is. It's slightly more complicated. It's actually a lot more complicated, but we'll get into it here. So what is ANOVA? ANOVA is an inferential method used to test the equality of three or more population means. Our null hypothesis is going to be one of no difference. So the means will be the same. So if we're testing three means, the null hypothesis mean equals mean equals mean equals mean. And the reason why we have to do this is because we're checking sample means and not population means here. So if we knew the population mean, obviously we could determine if they're different. But we can use the method in 11.3, but that means we'd have to do it thrice, and that would just go into a table. So, I mean, I guess I'll show you this here because it's simple logic. So we have 1, 2, 3. We have to check if 1 and 2 are equal. So I guess that's one test. Then if they're not equal, we have to see if let's see if 1 and 2 is equal. Let's assume they're equal. Now we have to test 2 and 3. And then we have to test 1 and 3. And instead of doing it 3 times, let's just do it once, because this leaves room for error. And here's where analysis of variance comes in. And it's going to be a little abstract for me too. So why not use multiple t-tests? We can't test 3 pairs. There's a higher risk of false positives. We can remedy the situation with ANOVA. And I'm not sure what the logic here is, but I guess if you do things multiple times, it's going to be a higher chance of error. Not really sure why, but I guess that's what occurs. And as we said, you set the null hypothesis as the means across the mean, as that means are the same across 3 groups. So we assume the means are the same across 3 groups. It's null hypothesis. We have to disprove that using the alternative hypothesis. Make sure the data comes from independent, randomly assigned groups, of course, because we're testing homogeneity of means, I guess. But they should all be part of the same population, or not part of the same population. That's, I guess, what we're testing with this ANOVA. But we assume all groups have equal variance and that the response variable is quantitative. So it's quantitative here. And if variances aren't equal, we use the Welch's t-test for 2 groups only to measure how many individual t-tests we need, which is kind of what we did over here. We just use KC2. So using 3C2, the formula would be, let's use some simple combinatorics here. It would be 3 factorial times, wait, no, it's 2 factorial, 1 factorial, which is just going to be the same as 6 divided by 2, which is 3. And yeah, 3 here. So that's the formula here. Not sure why they put that, because we're not going to be doing those individual t-tests. You could do that if you want, though. It's just ANOVA is easier. ANOVA is more resistant to changes, so we can focus less on the normal distribution issues, like the central limit theorem, which states that the numbers of trials have to be above 30. But each one has to be generally normally distributed, which is required for ANOVA. So to do so, use something like StatCrunch, which sorts the data from smallest to highest and gives z-scores. Draw the plot with the x-axis being the point and the y-axis being the z-score. Draw the plot. If the data is normal, it will make a linear line, and if not, it will curve. So if we made a thing, and this will be z-score. No, sorry, I think this will be z-score, and then we have point. Apologies for my bad handwriting. And we'll go over here. So it sorts the data from each one, from smallest to highest. And using some simple logic, we should be getting higher and higher z-scores. Getting a linear line. But I guess more of the points will be concentrated around this area right here. And then it'll be going up like that using simple logic. So we do that for each one. If that is normal, we'll make a linear line. I'm sorry, for not each one. I mean, I guess you put it into each one. So if your correlation value is close to 1, your data is normal enough. That just has something to do with empirical rule, so you'll be fine there. So how does it work? So it's a lot of work, and honestly, you could just use a calculator for ANOVA. But we have the overall mean, which is all data points divided by values, total sum of squares, which is each value minus overall mean to the square root of 2 summed for each individual mean. group means are the means of each individual group, or sorry, each value minus overall mean squared, and then we have the group means being the mean of each individual group. The between group sum of squares, which is group minus overall mean squared times sample size. Within group sum of squares, SSE is each value minus group mean squared summed. Degrees of freedom is just groups minus 1, and within groups is values minus groups, number of values minus groups. And mean statistic is MSA equals SSA divided by degrees of freedom, and MSE is the within group sum of squares divided by degrees of freedom. It's really complicated, and I'm not sure. I guess, I mean, every stats professor would probably just want you to use a calculator here for ANOVA. But this is kind of the steps, and you see here that they build on each point. So overall mean is all data points divided by values. We find it, we plug it into here. And after finding the total sum of squares, we can plug it into total sum of squares. We have to find somewhere else. It's definitely in here somewhere. The group means will be means of each individual group. We use the SSA over here, and then we also use the SSE over here. They all build on each other, so just calculate each one, and you'll find the F statistic. And once you get the F statistic, you find the corresponding critical value and degrees of freedom within groups. If it is greater than the critical value, it's unlikely. It's too many standard deviations away. I'm sorry, not. I guess it's too many MSEs away, which I guess it's mean squares. Not sure. It's mean squares. Mean within group sum of squares away. And basically, I'm not going to try to explain it because honestly, I have no idea how they found the ANOVA or how it works. But this is just the formulas you use. If it's greater than the critical value, we reject the null hypothesis. So that means are the same. So if it's greater than the critical value, we assume one is different. One or more, actually. I believe it could be just one. No, it's one or more. Different. If it is less, then we can assume that they're all the same. And we can also just use the z-score method as well instead of the f-score method. So we just calculate the critical value and use that. So that's all it is. And it's not simple, but you have a calculator and that has all the formulas on it. So